Okay, here we go with lesson 3, the last of our differential equation solving techniques. This form here, y dash is a function of x multiplied by a function of y. So the aim is to learn how to solve that form and to understand the related terminology, a separable differential equation. And the exercise is straightforward, it's just questions on applying this skill. Right, question 1, let's get into it. Y dash is 2x over y squared, so you might expect, we're going to rewrite that. Y dx equals 2x over y squared. Now, what can we do with that? We've got x's and y's all mixed up here. Well, if I wrote, let's say, a over x equals b over y, so if one fraction equals another fraction, then it's not beyond you to think that the next line I might write is ay equals bx, right? We're multiplying, what we're really doing is we're multiplying both sides by xy, and that's what happens here. Right, so we've neutralised all of the fractions in one go. Well, we can do the same thing here quite profitably. So we get, I'll just write dy times y squared equals 2x times dx, okay? And of course it looks better if we write y squared dy equals 2x dx, okay, but I'm just pretending it's a normal equation with fractions, and the thing is, it works. We can do this. Okay, so yeah, I'll not normally do that. And now that we've got this, which actually means something, I'd love to talk about it, but I won't. We can just whack this big integral sign in front of it. I've accidentally changed pen colour, sorry. There we go. Integral of y squared dy equals integral of 2x dx. Okay, it feels quite weird doing that, because normally when you put an integration sign into an equation, you have to put the dy as well, but it's just weird how it was already here. Anyway, this is how you do it. These are all legitimate steps. Right, we're going to integrate both sides. What's the integral of y squared? Well, a third y cubed. Now, of course, there's a plus c, but I'm not going to do that yet. And the integral of 2x with respect to x, it's important, of course, that the x and the dx match up, is x squared. Now, I'm going to put a plus c. That's covered the constant from both sides. I'm just going to show you the alternative. I could have 1/3 y cubed plus c1 equals x squared plus c2, and then we'd have a third y cubed equals x squared plus c2 minus c1, but we've got no idea what either of these constants are, so we'll just call that plus c. Right, so yeah, get used to that we're integrating both sides, but we only need to put the constant on one side. Now, we don't have an initial value here or anything like that, so we are just solving generally. So we'll just make y the subject. Y cubed equals 3x squared plus c. All right, a constant times 3 is still a constant. I don't have to call it c2. I don't have to call it 3c or anything like that. It's just a constant. And later on, if some information is provided that the curve goes through 1, 4 or something like that, then the constant will be found, and the equation will be found. And so y equals the cube root of 3x squared plus c. All right, question B. All right, so there's nothing more to be done here, and there's no plus or minus, nothing to worry about. Okay, so what did we do? We separated the variables. That's what it's called. That's why there's this terminology, a separable differential equation, right? We separated, we've got dy dx here, and sorry about that. We've got dy dx here. we separated the dy and the dx. So we do what we have to do to get all the x's on one side and all the y's on the other side, and that includes the dx and the dy. Okay, let's just want to make a point though, get my highlighters out. So we've got a function of x times a function of y. And here, well, right, in this case, y dash equals 3x squared times y. There's clearly the function of x times the function of y. In this case, though, when we have, we really have y dash equals 2x times 1 on y squared. If I wanted to be explicit about this, there's my function of x times my function of y. But what I want to be clear about is it's not the form itself that's so important. What's important is that we can separate the variables to go from this to this, okay? So you've got to look at when you're thinking, how am I going to differentiate something? Really, you've just got to think, can I just get a primitive? Can I take reciprocals? Will that help? Or can I separate the variables? Those are the three things. Okay, so we've got y dash equals 3x squared y. So we have, right, so dy dx. Once again, we need to write it as dy dx, or else we can't separate anything, 3x squared y. To separate things, well, I get this, dy times 1 on y equals 3x squared dx. Can you see what's happened there? The y has come over here and been a 1 on y, and the dy, well, that was in the numerator, so that's fine. And then the dx makes its way over here. We've sort of multiplied by dx, and the 3x squared didn't have to go anywhere. Okay, so the 3x squared didn't go anywhere, and the dy didn't go anywhere. Okay, but this y, okay, this y did have to go somewhere, so it became 1 over y, and this over dx, this 1 on dx, if you like, it crossed the equals bridge and became dx. Okay, I'm sorry if that seems babyish, but just, when students are not in front of me, I need to make sure I've explained everything as much as I possibly can. I'm going to have one more go at that. Dy dx, I keep going back to this colour. Right, dy dx equals 3x squared y. What can I do? I can maybe go dy equals 3x squared y dx, and now you've got to do something about that. So dy over y equals 3x squared dx. Okay, and that's a good place to end up. So I'm just saying that if it seems difficult, then just take an in-between step. Right. Off you go. And we'll get on with it. Right, and so we'll take the integrals. So integral dy on y equals integral 3x squared dx. Right, what's the integral of dy on y? Well, it's log of absolute value of y. And this x cubed plus c. Right, so we're going to exponentiate both sides. Absolute value of y equals e to the x cubed times e to the c, just applying some index laws there as well. You know what we're going to do next. Right. Okay, so a equals e to the c. And what do we do about this absolute value? Well, y equals a e to the x cubed. Looks like I've done nothing really, but now a greater than 0 or a less than 0. Do we have a trivial solution here? Well, if y equals 0, looks like a trivial solution, doesn't it? So that means that this y can be 0 as well, so or a equals 0. All right, so now we've got given 0, 1 here, so if we substitute 0, 1, and we get 1 equals a e to the 0 cubed, so a equals 1, and so y equals e to the x cubed. Done. Okay, next one. General solution to f of f dash x. Okay, so as we've seen a couple of times, just going to note that we have a function here, so we'll just make sure our answer is a function, and then find that. Okay, so dy dx, x squared on y. We've got a fraction, so we can sort of cross multiply here. X squared dx, integral of y dy, integral x squared dx, half y squared equals a third y cubed, not y cubed, third x cubed plus c, so that c is taking the hit for both sides. We've got y squared equals 2/3 x cubed plus c. Right, we've doubled a constant, but it's still just a constant. And so the general solution is really what I just wrote. All right, it's a relation, not a function, so writing it in terms of y squared is fine. Now, of course, right, the square root of that. Now, the particular solution, well, we have y equals plus or minus the square root of 2/3 x cubed plus c, and, well, if you look at the point, given point 3, -2, okay, this has to be, it has to be the minus, doesn't it? Okay, so right, y is less than 0, and so it must be the minus. The positive branch of this cannot produce a negative value. Right, we still haven't found c yet, so we'll put in -2 equals negative 2/3 of 3 cubed plus c. And, right, so 2, well, I want to get rid of the square root as well, equals 2/3 27 plus c. And that's 18, and that's 4. Okay, c equals -14, and so y equals, not plus or minus, because we established here that it's a minus square root of 2/3 x cubed minus 14. Okay, now that's done. This here turned out to be messier than I'd like. When I did my working beforehand, I used this to substitute 3, -2. That's just as good. You can get the c equals -14, and then you can do the rationalisation about whether it's the plus or the minus. You've already got your value of c. It doesn't matter. Okay, question 3. Which of these differential equations are separable? So, which ones can be separated? Now, it looks obvious to me that the answers A and C, because they have two terms. And my intuition, of course I've done the answers, but when I looked at it at first, my intuition was, well, you need to have two terms. This one is just a little bit too inseparable. But intuition is not the same as a firm answer, so let's have a look. Best way to answer it, in my opinion, is just to try to separate them. So in this first case, we have 5y cubed dy equals 2x dx. That's very separable. All right, let's look at this second one. Well, let's get dy dx by itself. So xy minus sine y. So, well, we can separate the x, so the dx, so dy. So because there's nothing obvious here to do to separate, I'm taking it one step at a time. Xy minus sine y dx. And now I can't have y's on this side, and I just need to correct that. That's sine x. Okay, so this y is a problem. So if I divide by y, then the left-hand side looks beautiful, and this, so far so good, but now, problem. So, no, there's nothing I can do to truly get the x's and y's apart. Finally, this one, x dy dx equals 2y. So I guess I'll just write this, dy dx equals 2y on x. I feel like we've seen something like this before. And now, if I cross multiply, I get x dy equals 2y dx. Now that's a bit awkward, isn't it? And so what can I do about that? Well, I'll divide by dy. How about that? X equals 2y on y dx. And now I'll divide by dx. X on dx equals 2y on... where did my... Sorry, this is dy here. That's good. Now, this here isn't good, right? You can't really have things on dx, but luckily I can just take reciprocals, so dx on x equals dy on 2y. Okay, so long story short, yeah, it's separable. Now I'm just going to go back to my notes here. Okay, and I'm going to do this again. It's fitting that this has remained behind, because what I've got here, I've got x in my notes, x dy dx equals 2y, and then, no, this is not fitting at all, actually, I'm sorry, 2y over x, and then I just put a tick. Obviously, it must be something that we've done before. No, it's not. Anyway, sorry about that. So my long way of doing it before showed that it is separable anyway. And so what's the important thing here? The important thing is that you are comfortable with that terminology and how to answer that question, because that could be a very, like it's a very easy multiple choice question for an examiner to write, isn't it? Okay, our last question. Just like last time, we're including a Cambridge one that's got some more words in it so that we can make sure that none of it bothers us. This one does have a bit more algebra in it as well. Okay, so question A, right, so with the initial value problem, so we've got dy dx equals 2y on x minus 1, and show that the constant solution is not a solution of the initial value problem. Okay, So the constant solution is y equals 0, because then the left-hand side will be 0 and the right-hand side, because of the 2y in the numerator, will be 0. Okay, so what am I doing? Showing that it's not a solution of the... Okay, so y equals 0 doesn't work with this, does it? All right, so so what I've written, this is not consistent with y of 2 equals 1. Okay, you can't, this function cannot produce a value of 1. Therefore, y equals 0 does not solve the initial value problem. That's a recognized abbreviation. B, use separation of variables to find a general solution. Okay, so dy dx equals 2y over x minus 1. And we can, I'm going to put in, so dy equals 2y over x minus 1 dx. And then we'll get the dy, we get the 2y down there. So dy over 2y equals dx over x minus 1. I did it like this because I'm perfectly happy going from there to there, but I don't want to assume that all of my viewers are perfectly happy doing that. So we're going to integrate these, of course, and we've got a situation where it's a log on both sides. And this, I'm going to put my half out the front there, and so I get half log of absolute value y equals equals log of absolute value right. And how do you undo a log on both sides? Well, you raise both sides to e, or you exponentiate both sides. So e to the half on that equals e to the right. Now, what do we do about this? Well, this half is better off as a power in this case, at least according to my way of solving it. So that's e to the log of the square root of absolute value y equals, now we've got our capital A as usual for the a times, now e to the log of absolute value of x minus 1, the e and the log cancel, so we've got absolute value of x minus 1. Now, what is e to the log y? Well, of course, the cancellation happens there, and so we have the square root of absolute value y equals a x minus 1. Okay, and we can square both sides, and that'll make the absolute values go away. So we'll get y equals a x minus 1 squared. Right. Now, I'm open to having it pointed out to me that there was an easier way to do some of that, because that felt a little complicated. Now, we've got our general solution, hence solve the initial value problem. So y of 2 equals 1. So C, y of 2 equals 1, and we've got y equals, okay, just putting in my information there. If I put that in, then I get 1 equals a 2 minus 1 squared. So a equals 1, and so we get y simply x minus 1 squared. So quite a simple conclusion. Okay, now this is a final question. I do just want to show you something interesting about this. So I'm going to create a lot of room here. And y equals x minus 1 squared, and our original thing was that y dash equals 2x over y minus 1. Okay, now let's just explore that a little bit. Terrible. Not great either, but okay, that's what y equals x minus 1 looks like, x minus 1 squared. And I just want to choose a random point on here, one I prepared earlier, 5,16. Now, take yourselves out of this topic and answer the question, what is the gradient of the tangent at y equals at 5,16. Oops, didn't mean to undo that. Okay, how do you answer that? Well, you go y equals x minus 1 squared. Y dash is 2 lots of x minus 1 by the chain rule. I put, right? So no need for that. Okay, at 5,16, y dash equals 2 lots of 5 minus 1, which is 8. All right, and so we've found out that this gradient is 8. Okay, now there's a couple of things I want to point out here. First, a little aside. A gradient of 8 means, okay, and so dy dx equals 8 is saying that y is growing 8 times faster than x is at this point on the curve. That's what this means. And remember what we encountered last time. What if we look at dx dy? If we make y the independent variable, then here y is going up 8 in order for x to increase by 1. So this is giving some justification, just a bit of visual justification for dx dy equals 1 over 8. Okay, now that's not the main thing I wanted to show you, that just comes up. But psychologically, to answer this question of what's this gradient, and we're using year 11 calculus here, we're only thinking in terms of x, aren't we? But in the language of differential equations, here's the alternative. I suppose an alternative needs an alternative colour. So compare y dash equals 2y over x minus 1, given, okay? And the point that we're interested in is 5,16, given. So y dash, the y dash is defined in terms of x and y, and I have x and y, 2 lots of 16 over 5 minus 1, which is 32 over 4, which is 8. There you go. So if all I care about is gradient, I've got only that much work to do to answer this question, compared to actually having a function, having a function definition, differentiating it, and substituting. All right? Now, I'm not saying one's better than the other. I'm just saying it's interesting to have the gradient defined in terms of both x and y. All right? And so, as I've shown before, it leaves open the idea that at many different points on the curve, on the number plane, the gradient can be different things, right? And that's what we'll be looking at in maybe even the next lesson, or if not that, then the lesson after. Okay, see you later.